Okay, let's get right into it. We all have a medicine cabinet, right? But have you ever thought about what's going on inside those little pills and capsules? There's a whole hidden world of science in there, and today we're going to unlock one of its biggest secrets.
You've probably wondered this yourself. You take two different painkillers, both are supposed to do the same thing, but one just seems to kick in way faster. Are you just imagining it? Nope, not at all. The answer is right there. It's just way too small for us to see. You see, it all comes down to size. And I mean, it's about things that are really, really small. The secret isn't just the drug itself, but the size of the tiny little particles that the drug is made of. And here's why that's so important. Smaller particles can dissolve faster. That means the medicine gets into your system and starts working more quickly. But it's not just about speed. Particle size also affects how the powder flows when they're making the pills and even how long it lasts on the shelf. So for drug companies, getting the size just right is a huge deal.
Okay, so that leads to a pretty massive challenge, right? If these particles are microscopic, how in the world do you even measure them? I mean, you can't exactly use a tiny ruler. This is a seriously complex problem that calls for some very clever tools. And the toolkit scientists have is pretty impressive. We're talking about everything from super powerful microscopes that can actually see individual particles to really smart methods using things like sieves or even lasers. Each tool is like looking through a different lens, giving scientists a totally unique view of this invisible world.
And check this out. Some of these techniques rely on basic physics, like Stokes' law. The idea is simple. Big, heavy things sink faster in a liquid than small, light things. By measuring how fast particles sink, scientists can figure out their size. It's a really elegant idea, but as you can probably guess, it can be pretty slow. So let's see how things have evolved. So to really wrap our heads around this, we're going to compare two totally different methods. One is a classic, kind of old school technique, and the other is a super modern high-tech one. Think of it like comparing an abacus to a supercomputer. So on one side, you've got sieving. It's a physical method that measures weight. It's cheap, but it's also really slow and takes a lot of work. On the other side, you have laser diffraction. This uses light to measure volume. It's ridiculously fast, but yeah, it's also really expensive. Let's dig into how they actually work. Sieving is actually beautiful in its simplicity. Seriously, just picture sifting flour in your kitchen, but on a much more precise level. You have a stack of screens, and each screen has smaller holes than the one above it. You pour the powder on top, you shake the whole thing, and then you just weigh what got caught on each level. That gives you your size distribution based on weight. Simple. Now get ready for this, because laser diffraction feels like something straight out of science fiction. A stream of particles is passed through a laser beam. It turns out, small particles scatter that light really wide, while bigger particles scatter it in a much narrower pattern. A detector measures these light patterns, and then a computer does some crazy fast math and tells you the size of the particles based on the volume they take up. Okay, so we have two methods. One measures by weight, the other by volume. You would probably think they'd tell you roughly the same story about a powder, wouldn't you? Well, this is where things get really, really interesting. So let's ask this question directly. Can the very same sample of powder give you two wildly different results? The answer is not only yes, but it reveals something absolutely fundamental about how we look at data. All right, imagine we just count the particles. If we do that, this is the picture we get. Now, these sizes are in microns, and for perspective, a single human hair is about 70 microns wide. So when you see that over half the particles are just 2 microns, we are talking about something incredibly fine. Looking at this, you'd say, okay, my powder is overwhelmingly made of tiny, tiny particles. But hold on. Now let's measure the exact same powder by volume, the amount of space those particles take up, like the laser does. And whoa, the story completely flips on its head. Now, more than half of the powder's volume comes from particles that are 64 microns. The tiny particles from before, they've basically vanished. How is that even possible? This table shows us exactly what's going on. Look at those 2-micron particles. By number, yeah, they're over 50% of the sample. But by volume, they're a teeny tiny fraction, just 0.06%. It's like having a room with 1,000 ants and 1 elephant. If you count them, the ants totally dominate. But if you measure their total weight or volume, the elephant is pretty much the only thing that matters. So what's the big takeaway here? It's that you have the same powder, but 2 different truths. And neither one is wrong. One chart tells you what's most common, and the other tells you what's taking up all the space. The real science is knowing which question you need to ask and which tool you need to use to answer it. All right, so let's zoom back out. What does this mind-bending little twist in the data actually mean for that pill sitting in your medicine cabinet? Well, it means everything. This isn't just theory. This level of precision is what makes sure that when a drug company makes millions of pills, the first pill and the last pill are going to work in your body the exact same way. It's the hidden science that guarantees your medicine is safe and effective every single time you take it. At the end of the day, the goal for these scientists is to get as close to the absolute truth as possible. That's the holy grail in this field, to understand every single particle and how it all fits together, making sure the medicine you count on does exactly what it's supposed to. So the next time you pop open a bottle of pills, just think about the incredible journey of measurement and precision that went into that one tiny dose. It really makes you wonder, doesn't it? What other invisible science is shaping our world, just hiding in plain sight?